You know, there's this hidden principle at play literally all around us, like right now. It's in the fizz of your soda, the air we breathe, and it's even happening inside your own body. Today, we're going to pull back the curtain on this powerful concept called equilibrium.
Okay, so let's start with a really simple question that I bet you've asked yourself before. Why, why is there always that empty space at the top of a soda bottle, right? Are the companies just being cheap, trying to save a few cents?
I love this. It's so relatable. My mom used to say the exact same thing. But that empty space, it isn't about being cheap at all. It's actually a super crucial part of the design. And the reason, well, the truth is all about some really beautiful hidden chemistry.
All right, so here's how we're going to unravel this mystery. We'll kick things off with the soda bottle secret, then talk about why it's a two-way street. After that, we'll see what happens when you try upsetting the balance. Check out the equilibrium scorecard, and finally, get into why this all really matters.
All right, first up, the soda bottle secret. Let's finally uncap this thing and figure out what's really going on in that so-called empty space.
So to get that fizz, right, manufacturers force carbon dioxide gas, CO2, to dissolve into the liquid. But here's the thing, it doesn't all stay there. A bunch of that CO2 also exists as a gas in that empty space at the top. And this is where the magic happens. At any given moment, some gas from that space is dissolving back into the liquid. At the exact same time, some of the dissolved CO2 is escaping out of the liquid and back into the gas. It's this constant, invisible, perfectly balanced dance that keeps your soda fizzy right up until you crack it open.
Okay, so that idea, that constant, balanced back and forth, that's the core concept we're talking about today. It's a two-way street, and in science, it's called dynamic balance or dynamic equilibrium.
So what is dynamic equilibrium? Well, it's a state that looks totally still, dead calm on the surface, but underneath it is absolutely buzzing with activity. The forward process, let's say CO2 escaping the soda, is happening at the exact same speed as the backward process, which is the CO2 dissolving back in. So the total amounts of everything never change, but believe me, the system is anything but static.
Here, let me give you a great way to picture this. Think about a parked car. That's static. Nothing is happening. Period. True rest. Now, picture a swimming pool where the water is flowing in from a hose at the exact same rate that it's draining out. The water level? It never changes. It looks totally still, right? But water is constantly moving. That's dynamic equilibrium, a perfect balance of opposing forces.
So how does a chemical reaction even get to this state? Well, at the very beginning of any reaction, you've got your starting materials, the reactants, and they're busy getting used up to make the new stuff, the products.
And this process keeps going for a while. The reactants go down, the products go up, until something really interesting happens. The amounts of both just stop changing. They hit this plateau and totally level off. And if you were just looking at it from the outside, you'd think, okay, I guess the reaction's over. It just stopped.
But, and this is the key, that plateau is not the end. It's actually the beginning. It's the exact moment that equilibrium is born. The forward reaction, reactants turning into products, is now happening at the very same speed as the backward reaction, where the products are turning back into reactants. It's perfectly balanced.
Okay, so this begs a really fascinating question. If these systems are in such a perfect state of balance, what happens if we mess with them? What if we poke the bear? Well, this leads us to one of the most famous principles in all of chemistry. It's called Le Chatelier's principle, and honestly, it's super intuitive once you hear it. Basically, it says that if you have a system that's in equilibrium and you disturb it, the system will shift itself to counteract whatever you just did. It's like nature's rule. It resists being pushed around and always tries to find its balance again.
Let me walk you through how it works. Okay, step 1, a system is chilling in perfect equilibrium. Step 2, you come along and introduce a change. Let's say you dump in some more reactants. What happens? Step 3, the system immediately shifts to use up that extra stuff you just added. It's fighting back, and it keeps doing that until, step 4, a new equilibrium is established.
All right, so if systems can have different balance points, how do we actually measure this balance? Well, chemists, being clever, developed a kind of scorecard to put a number on it. It's a way to see which side of the reaction the balance favors. They came up with something called the equilibrium constant, or Kc. And it's not as complicated as it sounds, I promise. It's just a simple ratio. You just take the amount of products and divide it by the amount of reactants after everything has settled down into equilibrium. That one single number tells you the entire story of where that reaction's balance point is.
And it's super simple to read. If you get a big Kc value, that means the balance heavily favors the products. You're going to have way more products than reactants when everything settles. On the other hand, if you get a really tiny Kc value, it means the exact opposite. The reactants are what's dominant, and the reaction barely even bothered to happen.
Okay, so a fizzy soda, a swimming pool, some math, I get it. This can all feel a bit abstract. But trust me, this principle of balance is one of the most fundamental forces that governs our world. We're talking everything from huge industrial processes all the way down to life itself.
Just take pH, for instance. You've heard of that, right? The measure of how acidic something is? Well, that's completely determined by an equilibrium between ions. And this is absolutely critical for life. I mean, our blood uses these amazing equilibrium systems called buffers to keep our pH in a super tight, perfect range. If that balance gets thrown off, it could be fatal. So you see, this is way more than just some random chemistry lesson. Understanding equilibrium is the key. It explains why a soda stays fizzy, it governs how medicines actually work inside our bodies, and in huge factories, it's used every single day to tweak reactions to get the most product possible. It really is a powerful hidden principle that's running things behind the scenes.
And that leaves us with one final thought to chew on. We started this whole thing by realizing that a seemingly still bottle of soda is actually buzzing with activity. So it kind of makes you wonder, right? What other things in our world, things that look totally static and unchanging, are actually in a state of perfect, unseen dynamic balance? Something to think about. Thanks for joining me.